My presentation will concern the concept of dynamic adaptation gain, which is an efficient solution for improving the adaptation or learning transients. The work has been prepared in collaboration with Tudor Bogdana Eremitwaev from Bordeaux University, Bernard Vaux from X-Blue, and Gabriel Buch for GIPSA Lab Grenoble. The major objective is to improve the adaptation learning transients. Many adaptation learning algorithms have been proposed in the literature in the last 15 years. Some old algorithms have been rediscovered. Many algorithms differ just by the way that the equations are written. And probably all proposed algorithms try to improve the gradient rule. We propose a dynamic gradient rule for accelerating the adaptation and learning transients. Many existing algorithms appear to be particular cases of the dynamic gradient rule. Performance and stability issues in this context have been addressed, and comparative evaluation by real-time experiment and simulation have been provided. The structure of the parameter adaptation learning algorithm is shown in this slide, where you'll have an estimated vector of parameter, which at the instant t+1 will depend on the previous value plus a correcting term. Usually you use a gradient rule, which has a correcting term. It's the gradient or an approximation of the gradient of the criterion and of a criterion with respect to the parameters. And this is used with a minus sign. And alpha, it's adaptation gain. Now, we are proposing a dynamic gradient rule where the inverse of the gradient, it's first filtered by a dynamic filter, C over D prime, which will call the dynamic adaptation gain learning rate. Obviously, one can generate an infinite number of adaptation learning algorithms, and many existing adaptation learning algorithms can be expressed under this form. The performance and stability of this type of algorithm are related to the properties of the transfer function characterizing the dynamic adaptation gain. And we will study at a certain point in particular the ARIMA2 algorithm, where the order of this polynomial was limited to 2 for C and 1 for D prime. We'll start with an application in adaptive feed-forward noise attenuation, where we are considering a silencer, which is a device which is introduced in a pipe circuit in order to reduce the noise. Specifically, here the noise is generated by a loudspeaker. At the entrance of the silencer, there's a microphone, a primary microphone, which provides information about the incoming noise. And the objective is to reduce significantly this noise at this level, which is called the residual noise, which is measured by a microphone. And in order to achieve this, we use a second loudspeaker, which is excited by the control signal, and the sound passes through, which is called the secondary pass, in order to minimize the noise at this level. Here you have an image of the results which can be obtained. The noise applied to the system was a broadband noise located between 70 and 170 hertz. This is a disturbance. And this is a residual noise measured on stream. And of course, there is an adaptation transient, and this appears clearly in the attenuation curve, and this gives an idea of the transient. Now we have done this for various type of algorithms, and we have put all the attenuation curve on the same figure. And here clearly we can see that the Arima2 algorithm is much faster than the gradient algorithm. And in fact, it's an acceleration by a factor of 2.5. We justify really to go into the detail of this type of algorithm. Now, let's look in detail to the dynamic adaptation gain filter, which is called HDAG, which in fact it's a diagonal matrix of identical transfer function. And we will look in particularly to one of this term, which is a single input, single output system. The numerator C, denominator D prime, with coefficients indicated here. Now, assume that the algorithm should operate for all frequency in the range from 0 to half of the sampling frequency. Let's assume that the gradient of the criterion to be minimized contain a single frequency. In order to minimize the criterion, the phase distortion introduced by the dynamic adaptation gain filter, this one, should be less than 90 degrees at all frequencies. And in order to achieve this, it results that the dynamic adaptation gain filter should be characterized by a strictly positive real transfer function. Now, there is a necessary condition for achieving this, namely the Pollenza zero of the dynamic adaptation gain filter should be inside the unit circle. But since they are inside the unit circle, it can be shown that the integral of the logarithm of the gain of the filter of the frequency domain, it's 0, which means the average gain of the frequency range from 0 to half of a sampling frequency will be 0 dB, it will be 1. So the consequence is that the average gain is still given by alpha. Here it's an illustration for 3 algorithms, the gradients, the I plus P, which I'll explain later, the Arima2. As we can see visually, you can realize that the average for all this algorithm of the gain is 0 dB. And in the meantime, these are positive real transfer functions, and the phase, it's between minus 90 to 90 degrees. Now, once we have understand the performance issue, let's look to the stability issue. To make this coherent, we'll realize the equation of the algorithm, which is given here, by taking into account that, in fact, we are feeding an integrator with this correcting term, and these two filters can be concatenated, and we express the algorithm in this format, where HPA is which is called the embedded adaptation filter, and it will have the format C over D, but specifically it's a concatenation of the dynamic adaptation gain filter with an integrator. Now, in many cases, the gradient is replaced by an approximation. So given a criterion of this form where epsilon is adaptation error, we often encounter an equation for generation of this error, which is a form of a filter which filter a scalar product between the parameter error and a regressor vector. So if we assume that this is the equation generated the error, often instead to use the gradient of the criterion, one uses an approximation, and this approximation is shown here. We neglect the influence of H, and this will lead to an adaptation algorithm which has this form. So the inverse of the gradient is here. Now, an equivalent feedback system can be associated to many adaptive control identification schemes. And assuming that the error is generated by the equations shown in the previous slide, where now theta tilde is a parameter error, then we can draw this equivalent feedback scheme, where we have a linear path which characterized by a linear fit for a part which is characterized by a transfer operator H, and the feedback path which is characterized by a filter HPAA multiplied by alpha between two multipliers. Now, asymptotic stability for any values of the adaptation gain will require two things. It will require the HPAA be a positive real transfer operator. This will assure the passivity of the equivalent path. And H, which characterizes the equivalent feed-forward path, should be characterized by a strictly positive real transfer operator to assure the global asymptotic stability. Now, let's look to a particularization of this dynamic adaptation gain, which we'll call Riemann 2, where the order of the dynamic adaptation have been limited to 2 for the numerator and 1 for the denominator. Associated to this, we have the embedded adaptation filter, which will be a second-order polynomial at the numerator, and of course, a particular second-order polynomial at the denominator. Based on the previous results, we'll need that the dynamic adaptation gain should be characterized by a strictly positive real transfer function for performance, and the embedded HPAA filter must be positive real in order to ensure stability for all value of the adaptation gain. Criteria have been developed leading to closed contour in the place C1, C2 for gain value of D1 prime in order to achieve this specification. So let's see here the diagram for the particular case where the coefficient D1 prime is equal to 0.5, but the diagram is similar for the other values. Now we distinguish first two curves. The first in blue defines the domain where the dynamic adaptation gain is characterized by a strictly positive real transfer function. The contour in black define the domain where the embedded adaptation filter is positive real. And we observe here that the intersection is not complete. We have a region here where the positive real condition for the embedded filter is not strictly positive real. So if we are in this region, we'll get a significant performance improvement with respect to the gradient algorithm, but will be guaranteed stability only for low adaptation gain. If we are now inside the black contour up to the intersection with contour from dynamic adaptation gain to be strictly positive real, we'll have a performance improvement with respect to the gradient algorithm, which will be less significant than in the previous case, but it will operate stable for high adaptation gain. And now this corner here is very curious because it will lead to poor performance with respect to gradient adaptation algorithm, but will tolerate very high adaptation gain for stability. Now, once we have understood how to design this algorithm, it's interesting to try to review, to survey various algorithms existed in the literature, and you will use as a basis the ARIMA2 algorithm just previously discussed. And we can say that the existing algorithm can be first divided in two classes. Integral moving average algorithm, where this coefficient will be 0, and autoregressive integrator algorithm, where the coefficients of the numerator will be 0. So in the first category, we have integral plus proportional algorithm characterized by the fact that C1 it's different from 0, but C2 is 0 and D1 prime is 0. We have the integral plus proportional plus derivative algorithm where both C1 and C2 are different from 0, but D1 prime it's 0. And we have which is called the average gradient, which is similar to the integral plus proportional plus derivative, except that we eventually can have more parameters than 2. Now, the autoregressive integrator algorithm, in this category, we have the conjugate gradient, where C1, C2 is 0, D1 prime is different. We have the Nesterov algorithm, which is similar. And we have the momentum propagation, where in addition to selecting a coefficient, the adaptation gain is modified in this way. So we can see that the ARIMA2 algorithm, it can be viewed as a combination of this algorithm with a conjugate gradient or with the Nesterov algorithm. Now, in this slide, we have some simulation results related to the identification of this second-order model, which is excited by a pseudo-random binary sequence. And to evaluate the performances, we have considered an error, a quadratic criterion on the adaptation error, the square of the parametric distance, and of course the sum of the parametric distance. And probably the most significant figure to illustrate the operation of the algorithm is here. And you see that in reducing the square of the parametric distance, the ARIMA2 algorithm is much faster than the integral, the gradient algorithm. But however, the other algorithm also provide improvement with respect to gradient algorithm, even it's less significant than for the ARIMA2 algorithm. The question which is important to explain, to answer, is from where came the improvement in performance. And to explain this in a simple way, I have considered the experimental results given for the adapted feed-forward noise attenuation we have seen previously. We have presented this curve, which illustrates the evaluation of the attenuation, and where we have seen that the RIMA2 is much faster than the gradient algorithm, and that the I plus P algorithm is faster than the gradient, but less faster than the RIMA2 algorithm. Now, it turns out that the regress of energy is mainly located in the region 71-70 Hertz, for the simple reason that this has a characteristic of the disturbance which affects the system. Now, if we look to the frequency characteristic of the dynamic adaptation gain, we see that in this region, the gain of the dynamic adaptation gain for ARIMA2 is higher than for I plus P, which in turn is higher than of the gradient. And these are coherent with the result which are here. The algorithm which has the highest gain in this region will provide the best performance. To conclude, a generalization of the gradient rule has been proposed, and it's called dynamic gradient rule. The dynamic adaptation gain allows to significantly accelerate the gradient algorithm. Performance and stability issues have been investigated. Design rule has been established. Strictly positive real property of some transfer function playing an important role for performance and stability. Of course, for low adaptation learning rate, the positive real condition can be relaxed using averaging. And the new algorithm, ARIMA2, has been proposed and evaluated comparatively with other algorithms, both by simulation and by real-time experiments. Many improved gradient algorithms are particular form of the dynamic gradient rule. There are extensions of these results for the stochastic gradient, for the recursively square, and for variable step size limit square adaptation algorithm mainly used in signal processing. The main reference for this work are paper in Automatica and in Journal of Sound and Vibration. Thank you for your attention.